Okay, we're going to take a look at a couple of problems for you flat earthers. And one of the problems we're going to look at first is the Verrazano-Narrows Bridge. At the time it was built in 1965, when I was a kid, I read an article in the National Geographic magazine that said that at the time the Verrazano-Narrows Bridge, suspension bridge, was the longest suspension bridge in the world, and that the towers were, because of the curvature of the earth, spread apart further from each other than the base of the towers, and that the distance was roughly a couple of inches difference. So what we're going to do is we're going to take a look at whether or not that is a reasonable assertion. And the way we do that is by using a little bit of trigonometry. So we're going to, first we got the earth drawn here, and we're going to draw the Verrazano-Narrows Bridge to the best of my ability. But first we're going to find the center of the earth, roughly speaking. Maybe it could be a little better, maybe more like that. And we put one tower here, and we put another tower here. You're going to have to, again, forgive my lack of artistic prowess. Okay, so these towers are a height h above the ground, above the planet. Now, the road surface, and we're going to do our best here to draw the road surface. It slipped a little, but that distance is, we're going to call that x. So the tower, h, is 693 feet, and x is the road surface above the water, which is 228 feet. And of course, the bridge is a suspension bridge, so we got basically cables that hold the road surface up, and they string down. Remember, we had an engineer, John Augustus Roebling, who promoted the use of suspension bridges because of the advent of steel wire, or steel rope he called it back then. And what we're going to look at is this distance, this arc distance here, S. And we're going to compare that to, and we're going to try and draw this. Here we'll do the best we can here. This will be roughly parallel to the curve below. So we're going to call this S prime. Oops. S prime. Those are the arcs. And if we take these to the center of the Earth, and we divided the bridge in half, we have two triangles with the same angle. We're going to call that theta, or let's call it phi, and we'll call that phi. All right, and we're going to compare S prime, the arc S prime, to S, and we know that S prime, using a little geometry, is going to be equal to R prime times 2 phi. And S is going to be equal to R times 2 phi. So that's all we have to do. Now, what we've done, basically, is we've got two triangles, like I showed, and the triangles, let's draw them here so we can best see them. Okay, so one other thing that we did look at is, see the road surface? That is the span of the bridge being suspended by the cables. And that span is L. And we can say L is equal to 4,260 feet. Now remember, we have to get everything into units of miles. Now, this triangle has L on 2 for one side, the opposite side to phi, and this is R and X. So the tangent of phi, is equal to L on 2 on R plus X. And that's how we get the angle for phi. Well, we have to put everything into miles, so R is the radius of the Earth, and that's 3,959 miles. I've rounded it up. It's actually 58.8, so I rounded it up to 59. But we have to put these into miles. So H is equal to, I got it all written down here. H is equal to 0.1 3 125 miles. X is equal to 0.04031818 miles. L is equal to 0.8068182 miles. And you can see 4,260 feet makes sense that it's 0.8 because a mile is 5,000. 1 mile is 5,280 feet, and that's 1 mile. Okay, and so R prime is R plus H, so R prime is equal to R plus H, which is equal to 3959.13125 miles. And R plus X is equal to 3959.04031818 miles. Now we have pretty much all the information we need. Now, tangent phi is equal to, now L on 2 is half that distance, so L on 2 is equal to 2,130 feet, or equal to 0.403 miles. Well, 403, let's go a few more decimal points. Let's see. 4091 miles. Okay, so we have 0.4034091 divided by 39.59.040. Let's see if I got this right. Yeah. 3. We'll just leave it there. 4. Okay. Now we do the division here, and we've got tan of phi equals 0.0000 0, 0, 1, 0, 1, 8, 9, 5, 7. And then if we take the arc sine of the tangent of phi, we have phi equals the arctan of 0.000101895.7, and that's equal to 0.0058382 degrees. But remember, we have 2 for the entire arc. We have 2 phi. So 2 phi is equal to Hi, John.
Yeah, Peter, so what's going on?
They're doing more tests. He said that the tests that I went through, just a second. Okay, sorry about that. That was a little interruption there. So where are we? 2 phi equals 0. 0.0116768 degrees. And if we can convert it into radians, we have, which we multiply by pi over 180 degrees. We make the conversion. And so we have radians now. 0.00020379136 radians. And that's the key. So now we have the angle, we have our distances, and so we can calculate the arc distances, and we'll take a look at the difference. So let's not erase that. We'll erase this. We don't need that anymore. And so now here to get S, we have S equals 3959 times 0.0002039. Okay, we'll leave it at that. And that will equal to 0.806 80998 mile. And S prime, now S prime is R prime. Remember, we calculated R prime, so we have 3959 9.13125 times 0.0002039, and that equals 0.8. Okay. 068 36 67 164 miles. And if we convert both of these, S and S prime, into feet, we have S is equal to 4,259.95 66962 feet, and S prime is equal to 4260.097862 feet, and we take the difference. So S prime, S prime minus S is equal to 0.141 feet. And you multiply that by 12 inches per 1 foot, and that converts it to 1.69 inches. So there's a difference in length between the top and the bottom of the towers by 1.69 inches. Now, if you go to the internet and you ask this question on the internet, they're going to tell you that the difference, and we're going to write our answer here, S prime minus S equals 1.69 inches. We don't need this. You're going to find that the internet tells you that the difference is S prime minus S is equal to 1 5/8 inches. But that is 1.625. I believe that's, let's do that calculation just a minute before I can commit. Okay, 5 divided by 8 equals 625. Yep, so 1.625 inches. So round it off, it's approximately 1.63 inches, and mine is 1.69 inches, my estimate. Now, the reason they say 1 5/8 is that when you take my calculation and you just round it off to eighths, you end up with 5/8. So the answers are equivalent. Now, you can go to a website. There is a website that goes through this calculation, and it confirms my approach, and it gets exactly the same answer I get, and then they round it off in terms of eighths, and they get the same answer. So this is a pretty interesting problem, and again, it's a problem that the flat earthers can't explain, because when you as an engineer have to design something, you have to design it to precision specifications. What if you were 2 inches shy on cable? Well, then you wouldn't have a bridge, would you? You'd have to, these sorts of things have to be engineered very precisely, because they won't work otherwise. And so this is one problem concerning the curvature of the Earth. And actually, it's a problem that I remember from my childhood days. Of course, I didn't know trigonometry when I read the problem, but I do remember National Geographic going on about how the top of the bridges was 2 inches further apart than the bottom of the bridge. And so we pretty well confirmed that, didn't we? And so trigonometry is pretty neat stuff, isn't it? Love that. Now let's take a look at another problem, and this is one that you can actually confirm for yourself with the ocean. And let me see where my earth maker is. Oh, there it is. Okay. Now I'm just gonna get in the way here a second, and we'll make our Earth. And this one had a very practical application, because during World War II, I live on the east coast of the United States. Whoops. And starting in Delaware and South Jersey, along the coast, the armed services put towers along the coastline every mile or so to spot submarines and such, German warships, to see if there was a threat off the coast. And these little towers that they put were concrete towers about 30 feet high. So let's again find the center of our Earth. Again, this is not a precision thing that I'm doing, it's just conceptual. In reality, this circle would have mountains on it much higher. They say the Earth, when scaled down, is smoother than a cue ball, even with its mountains. Okay, so we will construct a radius and our tower. And let's say this tower is h, and this is the Earth's radius, and we have a war vessel, let's say an enemy vessel, that has a mast on it that is 100 feet high. Okay, So, let me try and do the best I can here. Okay, that's not too bad, given the fact that I'm not very good at drawing, especially on this board. That ruler is awfully slippery on this surface. Now, this is the mast of our warship, and let's say that's the mast, and the mast is equal to 100 feet high, and I'm in a tower that's 30 feet high. When I'm looking out over the ocean, what is this distance that I can first see, D, when I first see the top of that ship, the top of the mast of that ship? That's the question. What is D? Well, let's say this is the center of the Earth right there. What we do is a little trigonometry. We know that this height is the radius of the Earth. This is r plus the mast. This is r plus the height. Okay, so what we need to do is find this distance here to here. We're going to call that x, and we're going to call this distance here to here, we're going to call that L. And x, whoops, it's not writing very well, but x plus L is equal to D. Now I know I did this problem earlier, but we were looking at it again because I had a little trouble with the one aspect of the problem, and I want to do this a little bit more carefully. So, but first I want to get the screen back. Because I like to be able to see what I'm doing, what it looks like on the screen. Okay. Now, you can see here we have two triangles, and we want to find the distance x and L, and x plus L is D. That's when I will first see the mast of the enemy ship coming over the horizon. Think of ourselves as Frenchmen on the coast of Normandy around the year 800 AD, and we're looking for Viking ships. Well, when will we see the top of the mast of the Viking ship? And we've built ourselves a little tower. We did the same thing in World War II, as I mentioned. Built them. You can still see them. They're big cylindrical towers with viewing windows that stand about a mile apart, all up and down the Delaware coast, all the way between New Jersey and Maryland. And that's how the civil defense at the time watched for potential German U-boats and such that may land. In fact, U-boats did land on America during World War II on the shore. They know that for a fact. Okay, so what we do is we take a look at this angle here, alpha, and we'll call this one phi. All right, and what we want to do is calculate the distance x. So what we do is we have the Pythagorean theorem. We have x squared plus r squared equals r plus h squared. So x is equal to r plus h squared minus r squared to the 1/2 power. That's what x is. And if we expand this one out, we have x equals r squared plus 2rh plus h squared minus r squared to the 1/2. But we take these out because they cancel, and x is equal to 2rh plus h squared to the 1/2. Similarly, we have L squared plus R squared equals R plus M squared. And what we are trying to solve for is L. So we have L squared equals, and we'll expand it out, R squared plus 2rm plus m squared minus r squared. These cancel, and L equals the square root of 2rm plus m squared to the 1/2 power. So those are, we got that solved, and we know that m is 100 feet, h is 30 feet, and everything should be in miles. So, or we could do it in feet, but it's just much bigger. So 100 feet, let's see, I keep getting a 100 divided by 5,280 is equal to 0.01894 miles, and 30 feet divided by 5,280 is equal to 0.00568 miles. So x and r, remember r is equal to 3,959 miles. So we have 2 times 3959 times 0.00568 plus 0.00568 squared. And this is all square root. And that, when you do the math, is, okay, this squared equals, okay, we'll do this. This darn thing keeps getting a sign telling me it's going to install some 3959 times 0.00568 times 2 plus, well, this is going to be infinitely small. 0.00568 squared equals, and we take the square root, and that's 6.71 miles. 6.71 miles. Okay, so that's the one side. That's basically how far I can see to the horizon on the sea. Now for the other, and let's erase to give ourselves some room here. This board is small. I wish I had a bigger board. So we said x is equal to 6.71 miles. And we want to find L. So L is given by that. And given the fact that this is so small, this is essentially L. L is approximately 2rm to the half, because this squared is small, very, very small. So let's see. 2 times 0.0189 times 3959 and square root, and that is about 12.2 miles. 12.2 miles. Now this is the answer that I got last time, although I used the angles last time, but I had a little trouble with the getting the arc angle, because the arc distance, we wanted to see the arc distance, S equals R theta, and theta equals alpha plus phi. So here we have L over R is the cosine. Well, or we could say L over R is the tangent of phi, so L over R is equal to the tangent of phi, and that's equal to what was our, I erased our 130, that's M, and this is X, and L we said was 12.2, so we got 12.2 miles over 3,959 miles. And that's equal to, we'll do this, 12.2 divided by 3,959, and that's equal to 0.00308 degrees. That's a 0, sorry. Okay, so that's degrees. We want to get that in radians, so we go times pi, and oh no, wait a minute, we don't want to do that just yet. We'll just leave it at that. Now, on the other side, we want to find alpha, and we know that x over r is equal to tangent alpha opposite over adjacent, and that's equal to 6.71 over 359. Oh, I'm sorry. That's not degrees. That's I'm sorry. That's just the number, n. Okay, so I just want to make sure that I have it right. 12.2 divided by 3,959. Yep, okay. And this is 6.71 divided by 3,959. And that's equal to 0.00165 equals Q. And the arctan of these numbers is alpha. So alpha and phi, let's say phi equals tan -1 of 0.00308, and alpha is equal to the arctan of 0.001695. And that will give us the degrees. So we have 0.09711 degrees, and we got 0.03082 arctan, and that's 0.1766 degrees. Okay, but we need those radians, and so we'll do these in radians. So we have 0.1766 and 0.0971. That's 713.17 degrees. And that is theta in radians, we multiply this number by pi and divide by 180. This ratio, we multiply that number by pi over 180 to get radians. So we got 0.2737 times pi divided by 180, and that is equal to 0.0047769 rads or radians. So the distance was, the arc distance is r theta is equal to 3959 times 0.0047769, and that is times 3959 18.91 miles, 912 miles. That's the arc distance. But remember, d is equal to x plus L. That's the straight line distance, line of sight. And that's equal to, we've got 12.2 and 6.71. We got 1, 9, 18. So it doesn't make much difference. D is equal to 18.91, and that's about the same as the arc distance. Because it's so short, the curvature of the Earth doesn't really make much difference. If you think that's a significant number, well, actually it is a significant number, because no, it isn't. It's not a significant. Well, let's see. I don't think that is necessarily a significant number. Well, anyway, they do agree. And basically we could say it's approximately 19 miles at sea is how far we could see if we were in a tower 30 feet tall. So that's that problem. And indeed, when we see boats, we don't even have to be that far away. You know, if we live on a lake, you know, the surface of the water is, because water is fluid, and if we don't have a gravitational anomaly under the lake, that let's say the material under the lake is of average density, then we don't have gravitational anomalies pulling in different directions. The lake is going to follow the curvature of the Earth. So we know the lake's surface is going to follow the curvature of the Earth. We could do a little experiment here, and we could set up a laser beam or a platform, and we can look at your friend's boat 5 miles away with a scaling on the side, and to see how far down with a known height h above the water, how far down the boat we can see, how much of the boat we can see. That's something that you can do, and it's something you can do with a lake only 5-6 miles long. just a good set of binoculars should tell you that, and knowing exactly how high you are above the water, and to see how much, let's say you're chest deep in the water, and you're looking down the lake toward the boat. You're not going to see the whole boat. You're going to see that a portion of it is below your range of vision. So that shows you that the Earth is curved. I also heard that you can see the curvature of the Earth from the bridge that goes across Lake Pontchartrain down in the New Orleans area, because of the length of the bridge that spans the water, that you can actually detect the curvature of the Earth there. And I think it's probably the same effect, being able to, how much of a boat is below your range of vision. So those are two problems that we have in trigonometry that help us understand the utility of geometry, and it's tough for people who, I hear recently that there's an increasing number of people, I don't know if they're really cranks or not, who actually believe that the Earth is flat. And I think that's more of a movement, but I think there are some flakes out there, I guess, that who would really believe that the Earth is flat. But we can use these little experiments and prove it to yourself that you do, that the planet that we live on is indeed flat, and or round. I'm sorry, not round, but curved, because it's round in all directions. Now, the one little thing that the ancient Greeks did was measure on the solstice, on the summer solstice. They placed sticks, at noon on the summer solstice. The sun at the equator casts no shadow, and you know that the sun's rays are coming directly from above. I'm sorry, that's a very poor line. And now we have the sun's lines. Now the sun is so far away. Let's get a little better shot of the board and less of me. The sun is so far away that essentially all of the rays are coming at the Earth from one direction. When you are far away from the sun, it may make a difference, but the sun's rays there we go. Now when we're far away from the sun, the rays go out radially from the sun. But when you're a long, long distance from the sun, and you're very, very much smaller than the sun is so much bigger than the Earth, the rays coming to the Earth are pretty much parallel. The Earth is insignificant in size. So the solar wind and the light coming from the sun are pretty much parallel. And so we're looking at the light locally. Now, if we put a ruler right here at the equator, knowing that the sun's light is coming directly from above, and let's say this is our ruler, or our skyscraper, and this is our ray of light hitting the ruler. It's not going to cast a shadow. But if we had a ruler here, and again, the ruler is going to be perpendicular to the Earth's surface, and we got a sun ray that's coming in parallel, and this is our ruler, or our skyscraper. I always thought it would be pretty cool to make a skyscraper in such a way that it would cast a shadow in the city. And you can make a great big sundial out of the building as the Earth rotates. But this is at 12 noon on June 21. That's our summer solstice. The sun's rays are coming directly. This is the Earth's equator. And this is some latitude, let's say, I don't know, 40 degrees latitude. Our building, or our ruler, let's say our building is H, and this is H. We know the distance around, and we got the shadow. We can measure the length of the shadow. We know the shadow, we know the length of the shadow. We've got R and we've got H. So we know we can deduce the length of the shadow, X. This is just a hypothetical. Let's say this is 40 degrees. And this is our hypothetical X. Well, we know that the shadow is the sum of x squared plus h squared. Here, x squared plus h squared equals 0. And this is, and so we know that the length of the shadow, x, is going to be x equals r squared minus h squared. Okay, so from that we're able to calculate. Actually, what I did was a little bit backwards. What I should have said was, with this light, we know that we have similar angles. We have, using some of the rules of geometry, we know that this angle, we're going to call it alpha, and that's alpha. Those are similar angles. This is 90 degrees. We're assuming it's 90 because of the magnitude of the Earth's radius compared to the height of the building. We know this angle. We're going to call that angle phi. And this happens to be alpha. And we know this distance. We know the height of the building. So we have h. We measure x, the shadow, and that's the tangent of phi. So that tells us basically, because we've got phi plus alpha equals 90. Remember our right angle trigonometry. So alpha equals 90 degrees minus phi. And once we have this alpha, we know that we have an arc S equals R alpha, and if we know S, we know this distance, which we have calculated by measuring the distance over the surface of the Earth from the equator. We've measured it off. We marked it like the Romans or the ancient Greeks. We take this ratio and we can calculate the radius of the Earth. And that's approximately 4,000 miles. And they can then, from that, using geometry, we know that the circumference of the Earth is 2 pi r. So the circumference is equal to, of the Earth, 2 times 3.14 times 4,000, or that's equal to 8,000. 3.14 times 8,000. And so we've got the circumference of the Earth, and that's what the ancient Greeks did. And so 8,000 times 3.14. So we got 0, 0, 0, 32, 0, 0, 0, 8, and we got 0, 0, 0, 24. I got 0, 0, 0, 2, 11, 5, 25, and 2 decimal points, and we got the circumference of the Earth to be 25,120. But, you know, that we can round off to 25,000 miles, approximately. And that's what the ancient Greeks did. And so they had an answer long before Columbus. Even in Columbus's day, they didn't know the circumference of the Earth. They just knew it was big, but nobody really calculated it. But the ancient Greeks knew, and they just used geometry. And we used a little geometry and trigonometry. And I'm going to just see what the circumference of the Earth is at the equator by measurement. All right. Earth circum. All right. Well, they say the Earth's circumference is 24,901. Let's see if that adds up to what I've been using. 3959. 3950. Well, no. That's just the radius. That's the well, we're off a little bit, but not much. Pretty darn close, given the fact that all they had was a stick or a ruler to be able to measure a shadow. So they came out with a pretty close approximation of the size of the Earth. So this is the cool kind of stuff that you run into with trigonometry and mathematics, geometry. A little bit of knowledge of mathematics can help you understand a lot of stuff. Well, we've gone over an hour, and we've seen 3 problems, all relating to the Earth, the curvature of the Earth. And so if somebody approaches you with the idea that the Earth is flat, you can come back at them with a couple of these examples and problems that you can work out and show to your friend that the Earth is indeed round, or at least curved. If you slice it in any direction, the Earth is going to be a circle. And so the Earth is basically a big ball in space. It's a little flatter at the poles than at the equator, and that's as a result of the Earth's revolution. It's spinning on its axis. At the equator, it's roughly a tangential speed of about 1,000 miles an hour. Up at the poles, it's much slower, but that's tangential velocity. That's something that you'll learn in physics. Maybe we could even take a look at a problem like that, because it does have practical application. But right now the video has gone quite some time, and we looked at, I thought, were some pretty cool problems. And so this is Math Man wishing you all well.